Welcome to note set number 32, where we're going to finish off our discussion of using the Z-transform to analyze discrete time systems. And unlike what we've done previously, where we've had zero initial conditions, we're now going to allow ourselves to have initial conditions. So when we previously have been describing discrete time systems and using the Z-transform, we focused on the following two scenarios. The input could exist for all time, and since it could exist for all time, you can't really think of initial conditions if the signal never really starts somewhere. And even if we did have a signal that started somewhere, we had been assuming that the system did not have any initial conditions, or in other words, they were set equal to zero. And that's a common view in areas like signal processing and communications, where the focus is on a signal comes in with some information and we're trying to modify that signal, extract the information, change the information, things like that. And for those scenarios, as we've seen, the bilateral Z-transform was perfectly well suited, and we found h of z and we found x of z using the bilateral transform, formed their product, did the inverse Z transform, and voila, we get the output signal. And that kind of analysis is perfect for signal processing and communications and things like that. However, we're interested in now looking at an area like occurs in a control system setting, where you've got a system that you're trying to control how it behaves, and it may already be doing something when you start to apply your input signal. And so because it's already doing something, it may already have some output values at the just prior to when you apply your signal. So if we assume that our input starts at time equal to zero, the initial conditions for a discrete time system become the output values just prior to the application of that signal. Now that's a little different than in the continuous time case. You may remember from your differential equations class that for a differential equation, the initial conditions are the signal, the output, its derivative, its second derivative, and so on, but all at time equal to zero, all at a single point in time. For discrete time, we don't have derivatives, so instead what we look at are successive output values just prior to the input. And depending on the order of the system, that determines how many of these we need in order to properly analyze the system. So for our use in this setting, when we want to include initial conditions, we break down, well, let me say it this way. We restrict our Z-transform explicitly to only include the parts that are not initial conditions. So only our applied signal and the output that arises after the application of the signal. So here I'm showing it with x of n, but we could just as easily have y of n, and I think I'll probably modify the slides before I post them to really put y's here, because it's really on the output side where we have this distinction. So what we're doing here is we're including in the sum only the parts that are occurring after we start to apply the signal, and we do not include the initial conditions. But we'll see in just a minute that when we start dealing with the delays that happen inside the difference equation, that we will have those initial conditions shifted into some one-sided Z-transform results. So that probably sounds confusing, but it'll be clear in just a minute. So most of the properties for the unilateral Z-transform carry right over from the bilateral form that we've already looked at. The main distinction is when we do right shifts and left shifts for that matter too, but we're interested in right shifts for our purposes. So let's suppose we have a signal x of n that's equal to 0 for all n less than 0. So this is what we call a causal signal. And so now the property that holds for that is exactly the same as for the bilateral, but this only holds for causal signals. So let's see if we can prove why that is. So here I've just expanded the Z transform equation to show some of the terms explicitly. And now I'm going to do the same thing for a shift by Q. And so what ends up happening is everything gets shifted to the right, and Q of these 0 values now get shifted in. So those are all sitting there at that point, but all of those are equal to 0, so we can throw those away, and then this is what we have left. But now what we can do is we can take this minus Q and this minus Q and so on and factor it out of each term, leaving behind the appropriate power to give us the right result. And then pull that z to the minus q out in front, and then we recognize that this thing here is just x of z. So we have indeed showed that if we have a causal signal and we do a right shift on it, the z transform of that right shifted signal is just z to the minus q times x of z, and that's because we're shifting in zeros. But things change when we do a non-causal signal. So now we have y of n is a non-causal signal, and I'm not saying the system is non-causal. I'm just saying that because we have this terminology non-causal signal versus a non-causal system, the output is considered to be a non-causal signal in this case because we now have some initial conditions that aren't coming from the input that we applied, but maybe from some previous input that had been applied. But the point is if this signal has some non-zero values prior to 0, we need to account for those. So now we take the one-sided Z transform. By definition, the one-sided Z transform, its sum starts at 0, so it does not include the impact of these things. So that's the beauty of this thing. It's allowing us to separate this into two different parts. The part that has the initial conditions and the part that is the result of applying the input. So here's a picture that shows some particular y of n with some non-zero initial conditions here. Actually, these would be the non-zero initial conditions, and then some subsequent values that occur after n equal to 0, presumably due to the action of the system. So if we were to take the Z transform of say this shifted thing, say shifted by 2, what ends up happening is 2 of these things that were not included in this sum now get included in the sum that is done for the unilateral Z transform of this shifted version. And so we need to account for that. So we're asking, what is the Z transform of this shifted signal when we have a non-causal signal? So let's just write this down, the resulting property for the first two values of Q, and we'll demonstrate where this comes from in just a little bit. But notice that for each of them we end up with the result that we've seen for the bilateral case and the result that we've seen for the unilateral case with a causal signal, that you multiply the Z transform result by Z to the minus whatever the shift is. But we also see those initial conditions coming into play. And that's how we'll get those initial conditions involved in our solution of our difference equation. We'll see that in just a little bit. And so now we can conjecture what the general result would be. So when we had 2 up here, we had a z to the minus 2, and then we had 2 terms where we had a z to the minus 1 and a z to the 0. So we can conjecture what that would look like. We're going to have a z to the minus q times y of z. Then we're going to have q terms here, and you can see that they go z to the minus q plus 1, z to the minus q plus 2, all the way down to z to the minus 1, down to z to the 0. So it's very easy to apply that, and you can see the order of the initial conditions. The y minus 1, y minus 2, all the way down to y minus q. So we need q initial conditions to account for this shift by q, and that makes complete sense. And so here's the quote-unquote proof for q equal to 2. So just like before, we shift this signal, except now instead of having zeros show up here, we have our non-zero initial conditions that are showing up there. So all this stuff over here we can treat like before and pull out a z to the minus 2, and we see that, aha, that's just y of z. But this is the part that gets shifted in, and that's the part that accounts for this stuff up here. So we can see that this result is verified, at least for the q equal to 2. And the most important thing is that we now have machinery that allows us to solve a difference equation with initial conditions. These are the mechanisms by which we include those initial conditions. So let's take a look at this, solving a first order difference equation using the unilateral z transform. So the z transform here is unilateral. And since it's a first order difference equation, and we know that by looking at the difference between the most advanced and least advanced terms. So for a first order difference equation, we need one initial condition. So that initial condition occurs just prior to application of the input, which happens at 0. So we're all set up, and what we're trying to do is find the output for n equal to 0, 1, and 2. And if you recall how we solved this thing recursively, and I just noticed I missed a negative sign there, how we solve this thing recursively, you'll remember why we needed only one initial condition, right? If we set n equal to 0, we set n equal to 0. To get y of 0, we need to know y of minus 1. So that's our initial condition that we need to know. So let's take the z transform of this I said differential difference equation. A lot of errors I need to fix in this. So let's take the z transform of this difference equation, and so here I've just done that in notational form. We know that we can use linearity and take the z transform right around that, and right around that. So that's our linearity. So we get that result. And we notice that that first term out in front is just y of z, and then this term here is just x of z. So on the right hand side we have b times x of z. But the question now is, what is this? Well, notice that we know that we have some value sitting over here at minus 1. So this is a right shift of a signal that is a non-causal signal. And therefore, we need the right shift property for non-causal signal. So our right shift property says not only do we have the z to the minus 1 times y of z, since we're shifting by 1, but we also have to include the one term that gets shifted in. So if we take this result and we plug it in here, then we get the following result. So this part here in the brackets is the part that we just found over here. Now, just like before, we see that we've converted our difference equation into an algebraic equation, and we can solve for y of z in terms of x of z together with little a, little b, and our initial condition. And so algebraically solving that, we get this, and I've manipulated this into two different terms. We could combine these, but it's important, I think, to to leave them separately so that we can understand their individual impact and what they mean. So notice that that this term here looks just like h of z times x of z. If you go back and look at the difference equation, that is the h of z, the transfer function for that. So that second term there is exactly what we've done before, and this term here we see doesn't depend at all on anything that comes from the input. There's no x of z in there. It only depends on system parameters. In fact, only system parameters on the left side. And most importantly, it depends on our initial condition. So the first term is the part of the output that's due to the initial conditions, and the second term has nothing to do with initial conditions. It has only to do with the input. So in a sense, we've been doing this all along, and we're now adding in some new term that accounts for the initial conditions. Now, we can manipulate this to get this into the z form. We've left x of z without any manipulation. If x of z itself came in the z inverse form, we would want to manipulate that also into the z form. So now once we have it in that form, then we can look at this, and this is just a constant out in front. This thing shows up on our z transform table. The root of the denominator ends up being this term here that becomes something raised to the n. So that's notice that that is actually the pole of the system, right? Here's the denominator of the transfer function, denominator over here. They are exactly the same. So the poles of the system describe the behavior in the time domain of this initial condition part. So if the poles are inside the unit circle, this initial condition part is going to decay with time. And that's a key thing that we would want to have for real-world systems. We wouldn't want initial conditions to cause our system to grow without bound. Unless, of course, this is a financial discrete time system and it happens to be describing our savings account. Then we would want it to be an unstable system and to grow without bound. And then this part is the part that we've been dealing with all along. So this is a really important piece of insight here, that we have our output in the time domain consists of two different parts. A transient part, assuming that the system is stable, a transient part that dies out and is completely driven by the initial condition, and then another part that we would get if we had solved the system assuming that the initial conditions were zero. And that's what we've been doing. So we already know how to handle this part. And these two parts just get added together, and so it's important to remember that when you have a system, linear time invariant system, with some initial conditions and an input, that we can think about the response of the system being broken down into two parts. One due to the initial condition, one due to the input, and we can handle those individually, and that makes the analysis very easy to do. So let's look at solving this particular, or at least a difference equation. I can't remember right now which one I put. I guess it's the same difference equation that we looked at before. And now we're going to assume that our input is a unit step. So we go to our table and we look up the unit step and find out that the input has that as its z transform. So using the general results that we just had for that first order, general first order difference equation, we plug in the x of z right here. Here is the part due to the initial condition. Here is the part due to the input, and this quantity here is our transfer function, h of z. And so now, whether we know enough to identify all those terms or not doesn't really matter. But we can now solve this thing using partial fraction expansion. I mean, in reality, we've already solved that first part. It's the second part that we need to solve. And so we would split that into a sum of two terms, one with a factor in the denominator z plus a, and one with a z minus 1 that comes from the input. And then these things up here come from the residues of our partial fraction expansion. And since we're doing this generally for an arbitrary a and an arbitrary b, it may not be possible to do this using some sort of computational, numerically computed way. We would have to do this by hand, although Wolfram alpha can do partial fraction expansion symbolically, so you could do it there as well. And MATLAB does have some symbolic computational capabilities as well, although I'm not familiar with how to do partial fraction expansion that way. So now we've got three terms. Each of them is on the table. I would like to point out something here. Notice that z plus a comes from our system. That's the essentially the characteristic polynomial of our system, and that sets what the pole of the system. So notice that that shows up both in one term from our input-driven case, right? So this was our input-driven term, and that got split into two parts. And z plus a also shows up in the initial condition part. I mentioned that once already. I'm mentioning it again. It's a really key piece of insight here. Now we just inverse transform each of these terms. We get something that has a minus a to the n. We get another term that's minus a to the n, and then we get a 1 to the n. So those are coming from there. And I could put u of n in here, but I've put in explicitly saying that this is true for n equal to 0, 1, 2, etc. What does it look like for n equal to minus 1? Well, that was the initial condition. We would have to be told what that value is. So this solution, this form here is valid only from 0 onward. But the important thing is that this part that's due to the initial condition and one of the terms that's due to the input, they both have this behavior that's set by where the pole of the system is. Now we also see that if the system is stable, that pole is inside the unit circle, and therefore this term would decay and this term would decay. So we have an IC-driven transient. We also have a input-driven transient that ultimately dies away if the system is stable. But then we have a part that is kind of persistent. Our input is persistent, and so our output should be kind of persistent in some way. Notice that 1 to the n is just 1, so eventually, once this transient dies out, the output is actually just following the input for this particular system. So this would be consistent with, you're probably familiar with, you go over to your wall and you adjust your thermostat to go to a higher temperature, and the temperature doesn't change instantaneously. It takes some time. That during that time, that's when this transient is happening. But after a certain amount of time, that transient dies out, and you're left with just a continuous operation, and that's the scenario where you've reached the desired temperature. Now, granted, that temperature example is not discrete time, but it's the same kinds of ideas. Let's go through same kind of thing for second order difference equation. We'll go through this a little bit quicker because it's very similar to what we just saw, but the results will be a little bit different, but the big picture will be the same. So it's the big picture that we really need to keep our eye on here. So we take the Z transform, and now we're going to use the right shift property for non-causal. So when we do that, we get one of the initial conditions included in, and when we take the Z transform of this term, we get both of the initial conditions included. And then we just need to do a little bit of algebra and move things around. And again, I've grouped it into these two different terms. One term that has the initial conditions defining the numerator. Another one that is a big thing that multiplies x of z. And notice that we know that this thing here is h of z. The thing that multiplies x of z is h of z, and we can pick that off by looking up at our difference equation. But the important thing to notice is that the denominator over here in the IC driven part is the same denominator as in our transfer function. So the pole characteristics show up over here as well as over here. So again, if the system is stable, that means that the roots of this are going to have magnitude less than 1. And when we do an inverse transform of that, we'll get things that will be decaying exponentially, and that's a good thing generally. Now, to focus on this part, we'd have to know what x of z is to do it further. But just like we saw before, we'll end up with one term that will have well, actually, in this case, we'll have two terms that will have the roots of those, or the factors of those, and then we'll have a term that's due to explicitly to the input. So let's take a look at just the IC-driven part first. And so here I've just grouped these two things together into a constant A, and then I've called this thing here B, just to make things a little bit easier to keep track of. Convert it into its Z form rather than Z inverse form. And then we look on our table and we see the bottom two entries on the Z transform table if we add them together. So we have a transform for this and we have a transform for this, exponentially decaying cosine, exponentially decaying sine. So if we add those two results together in the time domain, we'll add their two results together in the Z transform domain, and we get a general result that looks like that. And so that's exactly the scenario that we have here. If we look carefully, we've got a Z squared term, and we've got some big thing times a Z. That's what we've got there. And then we've got a quadratic in the denominator. So we can use this result, and we just have to match things up. So if we compare the generals to the specifics here, we can match all this stuff up and then apply that and be on our way. Now we also can recognize that with constant C1 and C2 out in front, that we can combine these cosines and sines into a generalized cosine that has an angle of theta. So the C1 and the C2 will contribute to determine what the C and the theta are. So right now it's not important that you know how to do all of that. We're just striving for some general insight into how the system behaves. So what that tells us is that a second order difference equation system will have this kind of potential behavior. And depending on what C is, what theta is, and also what A and omega 0, in particular what A and omega 0 are, they will tell us what the behavior of this is. Now, A and theta 0 tell us the poles. So the poles of this system will be equal to A e to the plus A e to the plus or minus J theta. J omega 0. So this A here tells us how close the poles are to the unit circle, and the omega 0 tells us where they are on the unit circle. So if omega 0 happens to be 0 or plus or minus pi, then this thing just turns into a constant rather than something that oscillates. So this behavior could be just a simple decaying exponential, or it could be decaying oscillations. So we can get either of those kinds of behavior from that. And we get these quantities from the parameters in the difference equation. So if A2, if the magnitude of A2 is less than 1, then we get a decaying response. So that's what determines whether this system is stable or not. But again, it's basically just whether the poles are inside or outside. So we've just gotten some good insight. Let's take this to the nth order case. We do all the same kinds of things. If we go through the same kinds of steps, we're going to end up with a term out in front where the a of z here is the characteristic polynomial that is the denominator term in the transfer function, and it also shows up as the denominator over here in this IC driven part. So this is all the same insight that we've seen before. And then if we interpret this general output result, and I'm just making some assumptions here for simplicity. If we have all distinct poles, when we transform this zero input part, the part that's driven by the initial conditions, we'll get a bunch of terms that look like this, where these describe the pole positions, and then those things get transformed into exponential terms. And if all of our poles are inside the unit circle, all of these things will decay down. And so that tells us that for a stable system, this initial condition part decays away. I've mentioned that several times now. That should be a clue that this is an important idea. The zero state part will consist of this product, where we're assuming that our input has some z transform that is just a ratio of two z polynomials in z. If we do partial fraction expansion and split all this apart, we'll see that there's one part here that's due to all the different poles. And again, I'm assuming discrete poles here, or distinct poles rather. And then there will be some other stuff here that comes from the partial fraction expansion, but it also retains that f of z. So this part we can make some assertion about. This part, it really depends on what the input looks like and how it ends up after the partial fraction expansion. But the big idea here is that this first part here is a transient part if the system is stable. All of these are going to be decaying exponentials if the poles are inside the unit circle. And so we call these two different parts of the zero state response. One part, this thing here, is called the transient response of the zero state, or the transient part of the zero state response, and this part is called the steady state response. It's what the system does after its initial transients die out. These are some really big ideas, and I try to capture them here. Again, I think it's more important that you understand the big ideas than you be able to than being able to just blindly slog through and get some numerical final answer, but not have a stinking clue as to what that means. Shoot for the understanding, and you'll be a much better engineer, and you'll be employable for a much longer period of time, and that's always a good thing. So the big things that we're seeing is that our system response gets broken down into two big parts. We've got the zero input part that's due to just the initial conditions. We've got the zero state part that is due just to the input, and then we can break those down further. The zero input part doesn't get broken down further, but we know that it behaves according to how the system poles tell it to behave. And if the system is stable, those terms will decay. They may decay oscillating, they may decay non-oscillating, but they will decay. The zero state solution, you can see that I'm using ZS to indicate that, has two parts: a transient part and a steady state part. The transient part is the part that comes from the behavior of the system poles. So again, those will decay if the system is stable. And you can identify those terms when you go back. You can identify those terms in the Z transform part by looking for the poles, the pole factors, or the factors that correspond to the poles of the system. And that will decay as long as the system is stable. Now this part is called the steady state part of the zero state response, and it depends on the interaction of the input with the system. And depending on that interaction, it might be persistent and just kind of hang around. Here's my trouble with my ink again. Or it might also decay. It just depends on what the input does. Obviously, if the input itself kind of decays away, then the steady state part will also decay away. So hopefully this provides you with some keen insight into how these systems behave, and we'll be looking at some of these as examples and problems during the class. Thanks. See you in the next video.